The last topic that I need to talk about is about cache performance and memory store cycles. Let me introduce this topic. We only have a few minutes left today, and I need to finish this topic, inshallah, on Sunday. Now, I need to talk about the hit rate and the miss rate. Now, when you access the cache, when the CPU access the cache, okay, either we have a hit or we have a miss. That's it. You cannot really have something else. Either we hit in the cache or we miss in the cache. So you can actually look at every access to the cache, and you can say this access is a hit or this access is a miss, like we have seen in the example. Okay. Now you can count the total number of hits and the total number of misses. That's actually, for example, you can write a simulator for doing this, and you can use counters to count the hits and counting the misses. Now, the way that we are defining the hit rate is the total number of hits divided by the total number of memory accesses, the cache access. So the total number of hits plus misses. And the miss rate is defined as the misses divided by the total number of hits plus misses. Very simple. That's the hit rate plus the miss rate. This is the hit rate and this is the miss rate. Now, if I add the hit rate plus the miss rate, what do you get? Add the hit rate plus the miss rate. What do you get?
Total number of accesses.
If I add hit rate plus miss rate, what do I get?
The total
One.
You get one.
Yeah.
Yeah. If it is not a hit, it has to be a miss, right? So if you have the hit rate plus the miss rate, you get one. And it is sufficient to know one to calculate the other. And if I tell you what's the hit rate, if I tell you the hit rate is 90%, what's the miss rate?
10%.
10%, yes. So it's easy, simple, right? So, so if you know one, you can calculate the other. Now we have more than one cache inside the CPU data path. We have seen there is an instruction cache and there is a data cache. The instruction cache is for instructions and the data cache is for data. So for this reason, we have to look at the, we focus more on the miss rate because the miss has a penalty. The hit will be excellent. Every time we hit, then there is no problem, okay? But there is a problem when we miss. So for this reason, our focus will be on the miss rate. Now we can look at the miss rate in the instruction cache, and we can look at the miss rate in the data cache. So for this reason, we define here two miss rates in the I cache and the data cache. And these are two different miss rates because these are two different caches. Here an example. Okay, I will just conclude with this example. I'll just take 1 minute. Now it says that out of 1,000 of instructions which are fetched from where? From where do we fetch the instructions? From where do I fetch?
Instruction cache.
From the instruction cache, yes. So when the CPU wants to fetch, it's going to fetch from the instruction cache. If the block is not found in the instruction cache, the cache will take care, the instruction cache will take care of transferring it from the main memory to the instruction cache. So it says that 150 missed in the I cache. So out of 1,000, 150 missed. So if they are missing, we are going to transfer them from the main memory. It says that 25% of these 1,000 are load store. So 25% of the 1,000, what's the meaning of 25% of 1,000?
250.
250, yes. So we have 25%, 250 instructions are load and store. And out of these 25%, 50 missed in the data cache. So only the load and the store will access data cache. So what is the I cache miss rate and what is the data cache miss rate in this example? Let us start with the I cache miss rate. What's the I cache miss rate?
150%.
Over 1,000.
So we divide 150 divided by
1,000.
Yes. So when we divide 150 by 1,000, we get 15%. Right. What is the data cache miss rate? Do all these 1,000 instructions are going to access data cache, or only 250?
250 only.
Only 250 are going to access because only the load and the store will address the data cache. The other instructions are not going to address. The ALU do not address. The branch do not address. It's only load and store are going to address data cache. So we have 250 are load store, and 50 out of these missed in the data cache. So what is the data cache miss rate? Quickly, please.
20%.
So what did you do?
50 divided by 250.
Exactly. So we are dividing 50 by 250, and this will give me 20%. That's it. What will happen? What will happen when we have a cache miss? When we have a cache miss, what happens? If I cannot fetch an instruction from the instruction cache, what will happen?
You mean doctor will generate address?
If the instruction is not found inside the instruction cache, what will happen?
It's like you will ask the memory.
Yes, but during this time, what will happen? Can we continue?
No.
Yeah, we have to wait. We have to stall. Exactly.
Yeah.
We have to stall the CPU. So this would result in memory stall cycles. So here we are talking about performance, right? So every time we have a cache miss, the processor is going to stall. If it cannot really fetch an instruction, let us say from the instruction cache, then there is nothing that can be done. So therefore, the CPU is going to stall, waiting for the instruction block to be transferred from the memory into the cache. The cache controller will take care of transferring this block, but during this time, okay, the CPU has to wait. The same thing happens in the case of data cache. For example, if the CPU cannot load the data, the program is going to wait for the data to be loaded into a register. So again, it's going to stall. So whether we have the cache miss in the instruction cache or whether we have it in the data cache, the CPU is going to stall, waiting for the instruction or waiting for the data. So now we need to count the number of stall cycles. Okay, how many cycles are wasted due to cache misses? So caches have negative impact. They can actually here reduce the performance of the CPU, especially when we have a lot of cache misses. So we can look here at the combined misses. Combined misses, it means that these are the misses in the instruction cache and the data cache. Okay, so that's the meaning of combined misses. So these are the I cache misses plus the data cache misses. So this is the meaning of the combined misses, and we multiply it by the miss penalty. Remember the miss penalty, I talked about it last time? The miss penalty. What's the meaning of the miss penalty? It's mentioned here, right? It's the number of clock cycles to process a cache miss. So every time you have a cache miss, it takes a certain number of clock cycles to transfer the block, okay, from the, let us say, from the second level cache or from the main memory. So it takes a certain number of clock cycles, and these cycles, the CPU is going to wait. So the meaning of the miss penalty is how long, how many clock cycles it takes to process a single cache miss. So we have to multiply here the combined misses. It's multiplied by the miss penalty. So we have to take into account the miss penalty, the time to process a cache miss. So in the case of the I cache misses, we can count all the instructions multiplied by the I cache miss rate, because every instruction has to be fetched. In the case of the data cache misses, we can count the load store instructions. So this is LS means load store, count multiplied by the data cache miss rate. That's actually how we count the data cache misses. Now notice that these same equations can be used to calculate the miss rate, as we have seen in the previous example. Yani knowing the I cache misses and knowing the instruction count, if you divide, you get the I cache miss rate. The same thing, if you know how many data cache misses and you know the load store count, this can be used to calculate also the data cache miss rate. So you can use them in different ways, these equations, depending, of course, on what is known and what is unknown, okay, in these equations. Now, to count the load store instructions, this is easy. Okay, the load store count, you need the load store frequency. And if you know, for example, let us say 25% of the instructions are load store multiplied by the total instruction count, this will give you the total number of load and store instructions in the program. That's the meaning of the load store count. Right. So let us take a look here at when people report, sometimes people report cache misses per 1,000 instructions in the program. Okay, so they report them per 1,000. Yani for example, they can say out of 1,000 instructions in the program, okay, that number of misses happen in the instruction cache, and this is the number of misses in data cache. So they report them per 1,000 instructions on average in the program. That's one way to report them. So now, if I would like to calculate, so what we have seen here in the previous slide is the total number of memory store cycles. But I can actually do it per instruction. Before I go into the example, I need to talk more about the equations. So the memory store cycles per instruction. Okay, so what we need to do is that we need to divide this by the instruction count. So here I have the memory store cycles. Okay, this is the equation for the memory store cycles. Combined misses multiplied by the miss penalty. If I would like to calculate this per instruction, I have to divide, okay, everything by the instruction count. So I need to divide the combined misses divided by the instruction count. It becomes the combined misses per instruction multiplied by the miss penalty. So here, this is the combined misses per instruction multiplied by the miss penalty. This is how I calculate the average number of memory store cycles per instruction. So what's important is that from the performance point of view is that to look at it actually from per instruction. Okay, how many memory store cycles, okay, we have per instruction. Now, there are some assumptions here that we are making to simplify the analysis of the performance. So the miss penalty is assumed to be equal in the instruction cache and data cache. Okay, so we're assuming them to be equal. Well, it does not really matter, really. In reality, it does not really matter whether you get a miss in the instruction cache or data cache. You have to transfer the block. And to transfer the block from the main memory into the instruction cache or data cache, it takes the same number of clock cycles. Okay, so it does not really matter where we have the cache miss. The second thing is that the second assumption is that the miss penalty is assumed to be equal for load and for store. Now that might not be the case, but in this analysis here, okay, I'm assuming that whether you have a miss for a load or a miss for a store, it does not really matter. We're going to assume the same miss penalty. Okay, so whether we are loading or we are storing, so we are treating the store like a load. So if you have a cache miss on a store, we are treating it like a cache miss on a load. So we're waiting for the block to be transferred from the memory into the cache, and we are actually writing to the data cache. So it does not really matter whether we have a load or a store. We are assuming the same miss penalty. Sometimes some hardware designers try to make optimizations in the case of a store to avoid stalling the CPU. Okay, and but we will not really go into these low-level details. Yes, Ali, Faddal.
Doctor, we can access level 2 cache memory, right? Or we
Right. Yes. So
like for example,
but
copy
that will complicate the analysis. I did not really want to go into level 2. Okay. So the equations become more complex when you are dealing with a level 2 cache. It means that we can try to reduce the miss penalty by introducing a second level cache. So the miss penalty here can be reduced by having a second level cache, and the second level cache will be much larger than the L1 cache, and we can actually transfer the blocks from the L2 to the level 1 without the need to go to the main memory. But if we have a miss in the L2, we have to go to the main memory. So that's actually why the equations are still become more complex in the case of level 2 cache. So for simplicity, we're going to assume just a miss penalty, which is a certain number. Okay, we can say that the miss penalty is, let us say, that number of clock cycles, okay, without worrying whether there is a second level cache or not. Okay, but of course it can be improved if we introduce a second level cache. Right, so now if I would like to look here at the combined misses, okay, per instruction. So notice that here we have, in this equation, we have combined misses per instruction. So we are looking at the combined misses and we are dividing it by the instruction count. So if I just go back to the previous slide, notice that the combined misses here is the I cache misses plus the data cache misses. So if you divide the I cache misses by the instruction count, you get the I cache miss rate. So when you divide by the instruction count, you divide the I cache misses divided by the instruction count, you get the I cache miss rate, right? That's actually is very simple. That's actually per instruction. In the case of the data cache misses, when you divide this by the instruction count, okay, you get the load store frequency multiplied by the data cache miss rate. Okay, so let us take a look at the equations here. So per instruction, when you would like to look at the combined misses per instruction, you look at the I cache miss rate because every instruction is fetched from the instruction cache. But then you look at the load store frequency, the percent of the instructions which are load and store, and you multiply it by the data cache miss rate. So that's basically how you calculate the combined misses per instruction. So you need it in this equation, and then you multiply it by the miss penalty. So now, if I would like to find the memory store cycles per instruction, just substitute the combined misses per instruction by this equation, which is shown below. So multiply the I cache miss rate multiplied by the miss penalty, multiply the load store frequency multiplied by data cache miss rate multiplied by the miss penalty. So that's my equation here, okay, that I need to use, okay, to solve problems, to find the performance. Okay, that's my equation. Here's an example on memory store cycles. Now it says that consider that a program, okay, has the following characteristics. The instruction count is 1 million. So we have 1 million instructions. 30% are load and store. This is my load store frequency. It's given 30%. That's 30% of the total instruction count. It says that the data cache miss rate is given here to be 5%, and the I cache miss rate is 1%. Usually we don't really get a high miss rate in the instruction cache because we fetch instructions sequentially. And basically we have loops and so on. So therefore the instruction cache miss rate is really very small. Now the miss penalty is very high. It's given as 100 clock cycles in this example. That's typically the case if we don't really have a second level cache and we have to go all the way to the main memory, then the miss penalty will be very high. It takes many clock cycles, okay, to bring a block, to transfer a block from the main memory into the I cache or the data cache. So it does not really matter where we have the miss. Okay, so whether we have it in the instruction cache or data cache, we have to go all the way to access the block from the main memory and transfer it, okay, into the instruction cache or data cache. We can reduce this miss penalty if we introduce a second level cache. So this is why people use second level and even third level caches today in modern CPUs. Okay. So the question is to compute the combined misses per instruction and the memory stall cycles. So how do I solve this problem? So there are two parts. Yes, go ahead, Ali. Fadda. So let us first calculate the combined misses per instruction.
Yes. First, we multiply the load and store with the percentage of D cache, and we sum.
Okay, let us start with the instruction cache.
Okay, it will be just 1%.
Exactly, 1%. So when we look here at the misses per instruction, so we have misses per instruction in the instruction cache, and we have misses per instruction in the data cache. So that's basically combined, okay, in the instruction cache, data cache. So when I say misses per instruction in the instruction cache, it's nothing but the 1%. That's basically is the miss rate, because every instruction has to be fetched. But what is the misses per instruction in the data cache?
To be multiplied. Multiply by 30%. Load and store by the D cache miss rate.
Exactly. We multiply the 30% by the 5%, because 30% are load store and 5% are going to miss. Okay. So to get it actually per instruction, we have to say actually how many instructions are actually load and store. So these are 30% of my instructions, and 5% of these 30% are going to miss. So That actually is the combined misses per instruction. So we got the 1% in the I cache. We got 30% multiplied by 5% in the data cache. So we got 0.025 combined misses per instruction. It is as if we are saying that out of 1,000 instructions, 25 are going to miss. And if you would like to actually convert it to misses per 1,000 instructions, this is why people sometimes refer per 1,000. So if you are fetching 1,000 instructions, okay, from the instruction cache, we will see that the 1% becomes 10 out of 1,000. 10 out of 1,000 is the 1%. So 10 of them are going to miss, okay, in the instruction cache, and 15. So we have out of these 1,300 will be load store, and 5% of these are going to miss. So therefore, we get like 15 misses out of the 1,000, okay, instructions. 15 misses are going to miss in data cache. So 10 are going to miss in the instruction cache. 15 are going to miss. So in total, we have 25 misses per 1,000 instructions. 10 occurred in the instruction cache. 15 occurred in the data cache. Okay, is this clear? So you can actually think about it as per 1,000. Okay, and this is just an average number. Okay, so that's the same thing as writing 0.025 misses, combined misses per instruction. Okay, of course, not every instruction is going to miss, but this is an average number.
We can make the percentage less if we have a bigger cache.
Yes.
I mean the solution.
If we use actually, yes, if you would like actually to improve the miss rate, you have to use actually bigger caches with more associativity. Of course, all of this will impact, okay, the miss rate. You can reduce the miss rate in different ways. You can actually have it set associative rather than directly mapped to reduce the conflicts and the replacement inside the caches. You can use actually larger cache with larger capacity. Definitely, you can actually reduce the cache misses and the miss rate. Yes. Right. So how about the memory store cycles? So we calculated the first part, combined misses per instruction. I need also the memory store cycles. How do I calculate this? Memory store cycles, very quickly.
Multiply the number of clock cycles.
What clock cycles?
Combined miss per instructions. We multiply it by 100 clock cycles.
Exactly. We have to look at the miss penalty. We have to look at the miss penalty because every cache miss has a penalty, right? That's the importance of the miss penalty. So when we miss, we are stalling the CPU according to the miss penalty. So don't forget about this. Okay, don't forget about it. So you have to understand these equations before you apply them. Right. So here we multiply the 0.025 by 100. So even though we have actually a small here, the combined misses per instruction actually is really small, but when we multiply it by 100, the miss penalty, that's a high miss penalty. You get 2.5 stall cycles per instruction, as if each instruction is stalling the CPU by 2.5 cycles. Of course, this is an average number. There is no half cycle here, but as if it is actually stalling it by 2.5 clock cycles. Every instruction. So you can see the negative impact on performance. Okay, why? Because the miss penalty is high. Okay, if I can reduce the miss penalty, I can improve the performance. So if I multiply this by 1 million instructions, so that the instruction count is equal to 1 million. Now we got it per instruction, but if you actually multiply it by the 1 million instructions, you get here, you can see 2.5 million cycles that are wasted. This is significant, right? We are actually wasting too many cycles because of these cache misses, and we have actually high miss penalty. Right. Any question about this, Ali? Tfadal?
Yeah, the miss penalty, Doctor, is 100 clock cycles.
Yes.
But after we multiply it by combined miss per instructions, we got 2.5 stall cycles. I mean, why we decide?
Per instruction, it's an average number, yes.
Why we which way we get 100 clock cycles?
This is given. This is given in the problem statement. It says that it says that given that the miss penalty is equal to 100 clock cycles. So this is actually measured by the circuit designers. How long does it take to access the main memory? Okay, and basically to access the main memory, this is actually measured in nanoseconds, depending, of course, on the delay inside the main memory. And it's actually converted, let us say, from nanoseconds to clock cycles, depending, of course, on the clock rate or the clock frequency, which is used in the CPU. So they found that it takes about 100 clock cycles. So this is, I'm just throwing a number here, but this is, of course, given in the problem statement as measured by the designers. How long does it take to transfer the block from the main memory into the cache?
Okay.
Okay, Ali?
Yes.
Okay. Right. So, so now, if I would like to go back to the performance equation, remember the CPU execution time? I talked about it before. So in order to look at the CPU execution time, we look at the instruction count multiplied by the average CPI multiplied by the clock cycle. But before, we did not take into account the presence of caches. But now we would like to take into account the presence of caches. And because we have caches and we have cache misses, we are going to store the CPU. So we have to take into account the CPI in the presence of memory clock cycles. Memory stall cycles. Okay, so the memory stalls here means that we are going to stall the CPU every time we have a cache miss. So that's the true CPI, because we have cache misses, because we are stalling the CPU. So this is the CPI in the presence of memory stall cycles. That's the meaning of CPI memory stalls. Okay, that's the meaning. But how do I calculate the CPI in the presence of memory stall cycles? Now we can assume that we have a perfect cache. A perfect cache means that everything is found inside the cache and there are actually zero misses. So the miss rate is zero. If you can actually have a perfect cache that has a zero miss rate, we call it perfect. Okay. So if everything is found inside the cache and there are zero cache misses, there is no need to stall. The CPU will run at maximum performance. Correct? That's actually the meaning of the CPI of a perfect cache. Okay, assuming that we have a perfect cache, no cache misses, that's the meaning of perfect cache. Okay, of course, this perfect cache does not exist, but from the analysis point of view, if we assume that we have a CPI here in the presence of perfect cache, and in all our previous analysis for performance, we assumed we had a perfect cache. We did not take into account the cache. So that's actually the CPI in the presence of a perfect cache. Now we might actually stall because we have like data hazards, because of control hazards, like in the case of a jump and the branches. But we did not take into account the caches. Okay. But what we have to do is that we take the CPI, assuming that the cache is perfect, and then we say plus. This plus is very important. So basically we add to this CPI, we add the memory stall cycles per instruction as we have calculated them in the previous example. Okay, that will give me the real CPI in the presence of cache misses and memory stall cycles. That's how we calculate now the new CPI.
Doctor?
This is an example. Yes.
But if we have a perfect cache, the memory will not be stale, right?
So basically, if I have zero cache misses, okay, the memory stall cycles per instruction will be zero, and therefore the CPI will be just CPI of a perfect cache. But because actually the memory stall cycles per instruction is not zero, because we have cache misses, then this is going to increase this CPI. That's what this equation means. So the CPI is going to increase because we have cache misses and because we have memory stall cycles. So we can actually calculate the memory stall cycles per instruction because the CPI is per instruction. Okay, so this is why we calculate the memory stall cycles per instruction. We add it to the CPI of a perfect cache. This will give me the true CPI in the presence of memory stall cycles.
Okay.
I have an example about this. which is shown in this slide. Now here it says that a processor has a CPI of 1.5. It says 1.5 without any memory store cycles. Okay, so basically, if you have a perfect cache, then this will give you a CPI of 1.5. So in all our previous examples, and when I talked about performance, we did not talk about caches. We looked at the CPI, assuming that the caches were perfect. So that's here the CPI, which is assuming that we have a perfect cache. So this is 1.5. So this is my base CPI. Okay, that's actually here which was shown in the previous slide. That's the CPI of a perfect cache. So when I say without any memory store cycles, it means that assuming a perfect cache, that's the CPI. Now the CPI here is greater than 1. It's 1.5 because we have still hazards. Like we have like data hazards, control hazards, and therefore sometimes we waste some clock cycles. Okay, we lose some clock cycles because we have to stall the CPU, or we have to introduce bubbles, or sometimes in the case of control hazards, like when we have the branches. Okay, sometimes also we lose some clock cycles. So the CPI is not really perfectly equal to 1. It's 1.5. Now, we would like to add to it the memory store cycles. We would like to add to this 1.5, we would like to add the wasted clock cycles, the memory store cycles per instruction. In order to do this, we have to look at the caches. So now we're going to look at the caches, and it says that the cache miss rate is 2% for the instruction cache. So when I say here for instruction, it means that in the instruction cache, and 5% in the data cache. So that's actually 2% in the I cache, and this 5% is in the data cache. Okay, and it says that 20% of the instructions are load and store. Okay, so that's my load store frequency. And again, the cache miss penalty is 100 clock cycles. That's a large number. Okay, 100 clock cycles. Okay, every time we have a cache miss, that's the miss penalty. That's the miss penalty. We should not really forget about the miss penalty. So what is the impact on the CPI? What shall we do?
1.5 plus the stall cycles for instruction.
Yeah, so what we need to do is that first we need to calculate the combined misses per instruction, and then we have to add to it. So we look at the combined misses. Sorry, we look at the combined misses. We actually multiply. You remember? Okay, so what we have to do is let us calculate the memory store cycles per instruction first. Okay. And then we add it to the base CPI, and this will give me now the new CPI in the presence of cache misses. So how do I calculate the memory store cycles per instruction?
Combined misses multiplied by miss penalty.
Okay, but combined misses, it has to be per instruction.
Okay, per instruction, sorry.
Yes. So how do I do this?
As we did, we calculate 2% for the instructions plus the 5%.
That's the 2% is given actually per instruction. Yes. Yeah. So when I say the miss rate, it's already per instruction. Yes, it is 2% in the case of the instruction cache. And we multiplied by the 100 cycles. We multiplied by the 100 cycles. Okay, for data cache.
Yes.
So for the instruction cache, it is 2% per instruction. And we multiplied by the 100 cycles, which is the miss penalty. So this will give me the memory store cycles per instruction in the instruction cache. In the data cache, because we have two caches, right? Inside the CPU, we have two caches, instruction cache and data cache. So in data cache, 20% are load store, 5% are going to miss, and the penalty is 100 clock cycles. So we can actually separate them into two parts. The first part is in the instruction cache. So 2% is my miss rate in the instruction cache. So this is basically the misses per instruction in the instruction cache multiplied by 100 cycles. In data cache, 20% are load store, 5% are going to miss multiplied by 100 clock cycles. If you want, you can actually combine them. Okay, you can actually combine the 0.02 plus the 0.2 multiplied by the 0.05. This will give me the combined misses per instruction, and then you can take everything and then multiply it by 100. You get the same result. You get 3. So it means that on average, as if each instruction in the program is stalling a CPU by 3 clock cycles. That's a large number. That's a large number. So that's the impact. This is because we have actually the caches are not really perfect, and because the miss penalty is 100 clock cycles. So notice that here a single cache miss is going to waste 100 clock cycles. This is a lot more serious than the case of branches and jumps and the case of, let us say, data hazards. It used to be like 1 cycle or 2 cycles. Now we are wasting 100 clock cycles. You can see that?
Yes.
So every time we have a single cache miss, we are losing 100 clock cycles. But not every time we have a cache miss, because we have a miss rate. And because of this, as if on average, okay, that each instruction on average is going to stall the CPU by 3 cycles. So this is the memory stall cycles per instruction. So these are cycles per instruction. So we have to add this 3 to the CPI because CPI is also cycles per instruction. So now we will say that what's the CPI in the presence of memory stall cycles?
It will be the perfect memory stalls plus what we got.
So we get instruction. So what is the result?
4.5.
Exactly. 1.5 plus 3 is equal to 4.5. So basically, we have increased the base CPI from 1.5 to 4.5. What does it mean to increase the CPI from 1.5 to 4.5? What will happen to the CPU execution time? If I divide 4.5, if I divide 4.5 by 1.5, what do I get?
1.5.
No, divide 4.5 by 1.5. What do you get? 4.5 divided by 1.3. We get 3. So you get 3. So what we are saying is that if I divide the 4.5 by 1.5, we get 3. What does it mean?
Execution is 3 times larger.
Longer. Yeah, so therefore the program is going to take 3 times longer. Yeah, for example, if the program took, let us say, 1 minute, okay, to execute and complete the entire program, now it's going to take 3 times longer. Okay, 3 minutes. Okay, so it is 3 times longer. So 3 times slower now. Okay, so the processor now is 3 times slower due to the memory stall cycles. Okay. So that's what it means. Right. So in the case of caches, it's good actually to define something which is called the average memory access time. So the average memory access time is the hit time. It's defined like this. It's the hit time plus the miss rate multiplied by the miss penalty. Now, notice that if the miss rate equal to 0, if this miss rate here equal to 0, the average memory access time is simply equal to the hit time. So the meaning of the hit time, it means the time to access the cache. Whether you have a hit or a miss, in fact, it's the time to access the cache. If the miss rate equal to 0, then basically the average memory access time, it is just the hit time. But because the miss rate is not 0, we don't really have perfect caches. Then what you have to do is that you have to add to the hit time, you have to add the miss rate multiplied by the miss penalty. Now you cannot just add the miss rate because the miss rate does not include time. So you have to multiply it by the miss penalty, which is in terms of clock cycles. So here's an example. It says that, okay, suppose that we have a cache. Now this average memory access time is a very good indicator of the performance of the entire memory system. Okay, so basically the memory system is a cache hierarchy. So start at the level 1 cache, and sometimes you can actually go to the second level cache and so on. So this is actually a good indicator. So the less the average memory access time, the better. Okay, so whenever we are dealing with caches, it's good to talk about the average memory access time. So in this example, suppose that the cache access time is 1 cycle. So typically people actually what they design is that the instruction cache or data cache They design the access time so that they can actually access it in one cycle. So this is why they keep the level 1 cache very small. They keep it small to keep it fast. Okay, and here the cycle time is given as 2 nanoseconds. That's the clock cycle. The miss penalty is assumed to be 20 clock cycles. If you multiply 20 by 2, it means 40 nanoseconds. And the miss rate per access here is the 0.05 per access. Now that's a combined miss rate. Okay, basically you can actually combine the miss rate. If you are dealing for both the instruction cache and data cache, okay, you can actually calculate a combined miss rate. Anyways, the question is, what's the average memory access time? We just replace the numbers inside the equation. So we have 1, if you would like to calculate it in the clock cycles. So it's 1 cycle is the hit time, so you put 1. The miss rate is 0.05. Now this is per access, not per instruction. That's the meaning here of miss rate, only when you access, okay? Not every instruction, for example, load and store instruction. So if you have an instruction which is not load and store, it does not really need to access data cache. So only load and store will access data cache. So for this reason, when we define the miss rate, we say it actually per access, okay? So we have here 0.05 multiplied by the 20, which is the miss penalty. So we get the result here as 2 clock cycles. So that's on average. That's my average memory access time. Okay. Now 2 cycles, if you would like to convert it to time, you multiply it here. The 1 cycle is 2 nanoseconds, so 2 cycles must be 4 nanoseconds. Now it will be much worse if you remove the caches, because it says that the miss penalty is 20 cycles. And if you remove the caches completely and everything is accessed from the main memory, and it takes 20 clock cycles to access the main memory, you have to multiply the 20 clock cycles by 2 nanoseconds. This will be 40 nanoseconds. So the entire thing will be much slower if you remove the caches. So the caches are trying to improve the performance and reduce the average memory access time. So that's the meaning of the average memory access time, and it can be quantified. We can calculate this average memory access time. So this is a very important equation. Now, next, I need to talk about how we can improve the cache performance. This is more like description. Okay, and briefly, maybe if I have time, I'll talk about just introduce multiple levels of caches. Let us go back to this equation, average memory access time. It has hit time, it has miss rate, it has miss penalty. People use it as a framework for making optimizations because we have 3 things. If I would like to reduce the average memory access time, I need to reduce the hit time. I need to reduce the miss rate. I need to reduce the miss penalty. So there are 3 things that can be done to improve the cache performance. If I would like to reduce the hit time, I need small caches. I need simple caches. This will reduce the hit time. If I would like to reduce the miss rate, I need a larger cache size. Because if you increase the size of the cache, you can have more blocks inside the cache and you can reduce the miss penalty. You can use higher associativity. You can use a larger block size. These are ways actually to reduce the miss rate. Finally, if you would like to reduce the miss penalty, you have to go to, the miss penalty here, then you have to go to multi-level caches. Multi-level caches, because if you can actually have a 2nd level cache, a 3rd level cache, there is no need to go to the main memory, and therefore you can reduce the miss penalty. Now notice that some of these are conflicting. To reduce the hit time, you need a small cache, but to reduce the miss rate, you need a larger cache. You see that these actually are conflicting. So for this reason, people actually use like multiple levels of caches. They use a small level 1 cache, and they use a bigger level 2 or level 3 cache. Okay. And to reduce the miss penalty, okay, they go multiple levels of caches so that you don't really have to go to the main memory. There are some details here in this presentation about reducing, okay, Like the hit time is critical because it's going to affect the clock cycle of the CPU. If you use a large level 1 cache, this is going to increase the clock cycle of the CPU. So for this reason, people actually keep the level 1 cache small and simple. If you use, for example, so there are some details here. You can see that I'm going to move very quickly now. So you can see that if you use directly mapped cache, okay, if the cache is directly mapped, you can overlap, okay, the tag check with the data transfer, because you have to make tag check to check. So you have to compare the tag against the tag which is stored inside the cache and data transfer. So people try to actually to design the cache and optimize its implementation in the hardware so that you can reduce the hit time to make the access to the cache as fast as possible. If you look at the size of the level 1 cache, it did not even increase much. And it's around like 16 kilobytes it was in the past. Today, maybe you can go to 32 kilobytes or 48 or 64 at most, not more than that. Okay. So that's basically the size of the level 1 caches. If you look, for example, inside real CPUs, there are tools actually that can show you, for example, what's the size of the instruction cache and the data cache inside the CPU. You can download some of these tools and it will tell you what's the size of these caches inside your computer system. Okay, so today in modern CPUs, it's still around like 32 kilobytes or 64 kilobytes at most. For the cache misses, now here it's actually interesting. What we need to do is that you need to reduce, okay, the miss rate. That's also part of the equation. So how do we reduce the miss rate? What you have to do is that you have to reduce the cache misses. So people have classified these cache misses into 3 groups. They said that we have compulsory miss. They said we have capacity miss. And they said that we have a conflict miss. So compulsory means that at the time when you start the program, the cache is empty. So definitely you're going to get a cache miss initially. Okay, so these are called cold start misses because the cache is initially empty. Okay, so the cache, what it will try to do is that's going to start when you get the first miss in the cache. Okay, some smart caches, they try to prefetch, okay, blocks even before they are addressed. So we have the word smart, okay? So basically the cache is trying to bring things, okay, from the memory into the cache even before the block is being addressed. So we call these compulsory misses because this is the first time the program addresses this block. It has not really addressed this block before. Capacity means it's related to the size of the cache. Okay, if you have a bigger cache, you have less capacity misses. So basically increase the size of the cache, you can store more blocks and you can reduce the capacity miss. So basically you can classify each cache miss. Is it compulsory, is it capacity, or it's conflict? Conflict, it's related to the associativity. If it's directly mapped or 2-way sub-associative or 4-way or 8-way. So if you increase, okay, the associativity, the number of ways inside the block, inside the cache, which means the number of blocks per set. So in the case of set associative caches, you can increase, okay, the number of blocks inside the set, then you have less conflict. If it is directly mapped, and every time you have actually a cache miss at a specific index, one block is going to replace the other. And if the program needs both, then it's going to cause many cache misses if it is directly mapped. So for this reason, people use, okay, set associative cache. Anyways, people have done a lot of simulation on caches and they found, okay, how we can reduce the miss rate. Okay, starting with one way means that the cache is directly mapped. 2-way set associative, it means that we have 2 blocks inside the set. Now notice that this small line here at the bottom, these are the compulsory misses. Now the one which is shown here in green, this is the capacity. Okay, that's related to the capacity. So as we increase the capacity of the cache starting from 1 kilobyte to 128 kilobytes, this is an experiment. Okay, basically this is done by simulation. You can reduce the cache misses. And so that's the capacity. And then above that, all of this is related. So when I say capacity, assuming that the cache is fully associative, okay, and you can actually place the block anywhere inside the cache. Above that, I have 8-way, 4-way, 2-way, and 1-way. So when we go here to actually to reduce associativity, we start getting conflict misses. So these actually are conflict misses that appear on top of the capacity misses. So you can actually classify these misses. So people try to do this. Okay. So anyways, okay, maybe I need to stop here. I still actually have few slides related to the block size. Okay, should we use a small block size or a larger block size? So today people actually use 64-byte blocks. I found that 64-byte blocks are optimal in level 1 caches. Sometimes they use 128 block size are also used in level 2 or level 3 caches. Okay, but to have a common block size actually simplifies the hardware implementation. Multi-level caches, we can go here from level 1 to level 2. And you can have an instruction cache and data cache. Both are at the level 1. And then there is a unified level 2 cache. So unified, it means that it contains blocks of instructions and the blocks of data. That's the meaning here of unified. So if there is a miss in the I cache, so first we go to the level 2. And if it is a miss in the level 2, we go to the main memory. The same thing for data cache. If there is a miss in the data cache, we go to the L2. And then if there is a miss in the L2, we go to the main memory. Okay. I don't really want to go into the details. This is an example of a chip from IBM. This goes back to 2010. This was actually the best, the high-end chip, okay, from IBM. It had 8 cores. And inside each core, we have 32 kilobyte for the I cache, 32 kilobyte for data cache, 3-cycle latency for level 1 cache. It has a 256 unified L2 cache. So that's the L2 cache. And it had 8-cycle latency. So basically, if you have a miss in the level 1 cache, you have to go to the level 2 cache. But the miss penalty is only 8 cycles, not 100 cycles like in the example. And then you can see in between all of these caches, there is actually a level 3 cache, which is shared. And it is 32 megabytes in this chip. Back in 2010, they had actually 8 megabytes. Until today, they have like 8 megabytes or 12 megabytes. This is in 2020. Back in 2010, actually, IBM was producing these kind of chips. But these actually are the high-end chips which are used on servers. Anyways, that's it for today. Okay, I just wanted to show to you actually some real examples. We will, if you are taking the next course, which is 403, I go into more details about caches and about multi-level caches